let's start. Before the lectures of automatic speech recognition, I'm going to make some clarifications on assignment 3. So first, where to apply softmax at the classifier head? The answer is after the classification. So we don't need to apply softmax before passing to the classification. Instead, we do the log softmax after the classification. So usually people do not care about the log softmax layer because they are using cross-entropy loss. And in PyTorch, the cross-entropy loss is essentially an NLL loss followed by, actually it's a log softmax followed by an NLL loss. But here in assignment 3, we are using NLL loss. So we need to apply a log softmax layer at the output of the classification head. And the second clarification is about model saving and loading. So in PyTorch, you can export the state dict and save it as a Python object to a file. You can use torch.save, get the model.stateDict, and save it to a file. And this file is represented by an object that can be acquired by open, the open command in Python. So you can call open path, and that command is going to return a file handle, which is f. So when you want to load the model, you can do first instantiate this model and then load the state dict. And this state dict is acquired from the previous step. So for that question in assignment 3, you can either directly run the Jupyter Notebook on the CS Lab server, or you can also run that, download the models and run them in your local computer. So whichever works can be accepted, and also in one of the questions, the submission format is a PDF file. So PDF file is very flexible. You can include the model's printing output. You can include text. You can include the code. You can also even include screenshot of the, for example, Cohere or the GPT-3 playground. So, but please do include sufficient information, including the some hyperparameters that you set, so that the other people, when seeing that report, is able to exactly reproduce to a large extent what you acquire. So please include sufficient information in the report. And also please include some discussions and make sure the discussions are not just at the superficial level. So the TAs will take off some marks if the discussions are not deep enough. Yeah, question?
Sorry, I wonder if you could at some point provide some more details on Piazza about what exactly we're expected to do, because I don't think in the assignment much attention is paid to the discussions in the handout. And now you say that they need to be deeper, or maybe an announcement for everybody at some point.
So the discussions don't need to be something that have something like 5 lines or 6 lines, but I don't expect to see some discussions that are as short as 2 words or 3 words. So these are 2 short discussions. So it really depends on which question that is. So in some questions, we ask you to comment on the performance of ChatGPT and just say, for example, in the question that asks you to comment about the performance of ChatGPT in solving the assignment problem itself, and a not acceptable comment would be ChatGPT is able to solve that, and that concludes the comment. So that comment is too short. So you should also point out what it is able to do and which part is not able to do. So and also if the model is not able to correctly recognize the sentiment or is not able to correctly solve this problem, you should comment on which part that model is not able to solve. So the overall point is to just show that you are actively thinking about the process. So actually, one of the very important theme in the future is that there will be a ton of human AI collaborations. So after you graduate, when you do the work, when you write the reports, when you write a lot of things, you are very likely going to use ChatGPT or some newer versions of the large language models. So these kind of models are very powerful, and it can save you a lot of time. But the qualities of the generations are still at some time questionable. So I want you to actually look at the outputs of the models and think about which part this model is able to do and which part it is not able to do. So in this way, you won't be kind of so you in this way you will still be able to take the responsibility of the contents that are generated. So currently, because the AI models are not able to be responsible, but humans are able to be responsible. So I want you to be able to take the responsibility when you are using the model to generate some output, and also the in the future, I think the quality of the generated contents are still going to be a pain point for the model developers. So this problem is not going to be solved in a short time, like as short as several years. So you still need to carefully check the output of the models to make sure that when you don't want the model to make mistake, the output is not incorrect. Okay. So another clarification is about the auto model for causal LM. So auto model for causal language model is still a sequential classification model, but different from auto model for sequence classification. The auto model for causal language models classification head projects the hidden dimensions onto the a dimension that equals the vocabulary size instead of the dimension that equals the number of class. So, and you can as another follow-up discussion on the Piazza, someone said that the output has another dimension, which is the sequence length. So that is different from the auto model for sequence classification. So that is because the classification head of the auto model for sequence classification only takes in the Pula output, which essentially is the output of the CLS token. But the linear head at the auto model for causal language model takes in the output of all the tokens and projects it to some probabilities. So you are able to see a three-dimensional output, which are the batch size, sequence length, and the vocabulary size. And this picture shows a more detailed elaboration of what we mean by the auto model for causal language model predicts the next word. So we can see that the first row, the purple sentence, are the input, and the green row are the labels that the auto model for causal language model predicts. So the green row is shifted forward by one token. So it means that for every single location in the input, the predicted output is exactly the next token. So for example, at this location, the inputs are transformers R, and the output, the desired output is grid, which is the next token here. So practically, the first token here does not really matter because there's no context to predict the first token at the label. So we mask them out. And the last token is especially interesting because the last token, there's no token that naturally follows the last token. So what this model generates, or what this model predicts, is the probability of the new token. So effectively, this model is the auto model for causal language modeling can be used to predict the probability of a new token given the previous sequences. And if we concatenate this predicting new token onto the end of the input sequence, then we're able to predict the next token after the new token. So this is the autoregression prediction scheme. And by repeating this scheme, we're able to generate long sequences. Question?
So is there a special token that denotes end of sequence? So how does this model know how to stop? Does it predict end of sequence and that's it?
It's essentially it's the end of sequence. So when it encounters the end of sequence, it stops.
Thank you.
Yeah. Any other questions about the sequence generation? So this kind of procedure is also present in the machine translation. But what's different is that in machine translation, you also condition on the source sequence in addition to the sequence that are already generated. And in the automatic speech recognition, you also see a very similar sequence generation scheme here. And automatic speech recognition is essentially a translation, but it's translating from speech to text. So any other questions about the auto model for causal language modeling or any other aspects of assignment 3? Okay, great. Let's start automatic speech recognition. So the contents for ASR will be split into 2 lectures. So today we're going to briefly introduce what is ASR and a noisy channel ASR model. I'll also describe briefly what the input and output of ASR systems are. And in the next lecture, I'll describe an end-to-end ASR model and how to evaluate the performance of the speech recognition systems. So nowadays, the speech technology has wide applications. They occur mostly in the format of smart assistants. We can, for example, tell the smart assistant to book a haircut for a client, or tell the assistant to tell a joke, or ask for example, Alexa to tell us about the weather, or we can even ask the assistant to put some product into our shopping list. And anecdotally, one thing that Alexa was criticized is that it really likes to put new products into your shopping list. Sometimes it can recommend some product and put into your shopping list. So because it thinks that based on your previous behavior, there is a really high probability that you are going to purchase this product. This might be a desirable thing, but some people really dislike that. Just saying. So here's a use case of why these automatic speech recognition technologies can be used. So if we ask a smart assistant in our phone, what is the weather? Then what we say out are essentially speech. And speech are essentially oscillations of the small particles in the air. So these kind of speech signals can be recorded as one-dimensional oscillations. And I'll describe what the data format of speech is in the next few slides. So with the automatic speech recognition technology, the smart assistant in the phone is able to transcribe that into text. So it's the transcription is, what's the weather? And the text is able to be processed by some backend systems, either at the server side or at the client side. And in this example, one solution at the backend is to query for the weather, and the returning string, the returning data consists of a JSON object. For example, temperature equals 325, unit is Celsius, and cloudy equals true. And when we convert that back to a text, then one example is it's cloudy at 3 degrees. Today's high is 5 degrees. And sometimes the smart assistant just shows you a text as output, and sometimes it uses another step, speech synthesis, to convert the text back to the sound and place that back to you. Speech synthesis is essentially another sequence-to-sequence translation. It translates from text to speech. So it goes to in the opposite direction from automatic speech recognition. So in this year's CSE 401, we're not going to the details of speech synthesis. We're just going to focus on automatic speech recognition. So ASR systems convert speech into text, and the input is speech data. So in the next few slides, we're going to describe the format of speech data. For now, let's just assume that speech data are numbers, and the output is text. I'm using W to represent the text. So one of the reasons is that in the next few slides, we're going to import an assumption that every single text only consists of one word. Another reason is that actually in the real world text contains multiple words, and we can handle the words in a standalone manner. We can also use some other neural networks to take care of the dependencies between the words. And in the simplifications of ASR systems, which we will describe in this lecture, we are going to just consider the text that consists of word, or that consists of one word. So the other name of the system includes speech recognition and speech to text. So in the previous lectures, we described some properties of text. For example, the features that we extract from the text. And we also described how to build natural language processing systems that can understand multiple aspects of the text. For example, the syntax, the semantics, or even some information that is not able to be carried through directly from the text, like those pragmatics or the common sense information. We even have 2 lectures that describe the properties of information and how to quantify the information and how to make decisions based on the information. So in this lecture and next lecture, we are going to describe speech recognition. So speech is essentially a modality of language. So it extends the text modality into speech modality. So what is the format of speech data? Speech data are essentially one-dimensional arrays, and the length is, let's use a symbol T1 to represent the length. So T1 is usually very long because T1 equals the sample rate times the time length. So sample rate essentially describes how many data points you have per second when you record the speech data. And T is the time length. It is how many seconds do you have in recording this speech data. So let's say you are recording at 16 kilohertz and you record it for 2 seconds. Then the resulting speech data will contain 16,000 times 2 seconds, equaling 32,000 numbers. So this would be a one-dimensional array with 32,000 numbers. So this is extremely long. Actually, one of the most advanced neural network system, GPT-4, claims that it's able to handle sequence lengths that are as long as 32,000. So, but 32,000 is only as short as 2 seconds. And when recognizing the speech, some speech samples of as short as 2 seconds are definitely not enough. So we need to be able to handle some much longer sequences. So the extraction of speech features are usually desirable. So the speech features are, let's say if you extract D equals 10 features or D equals 64 features, and these features are computed based on some time windows of, let's say, 1 second. So the length of the features are going to be a lot less than the length of the raw speech data. So if your speech features are computed in a window of 1 second, then T2 is going to be just equal to small t. Actually, usually the speech features are computed at the windows with sizes for a lot shorter than 1 second. It's usually 50 milliseconds. So for each second of speech data, there are, instead of 16,000 numbers, there are only 50 numbers times the number of features. So one typical type of features is the energy in the corresponding frequencies. So I will go into the details in the next few slides. And the tutorial is not going to be about MFCC feature. The tutorial is going to be about speech brain, and the TAs might also include some part of MFCC feature, but the feature called MFCC is not in the syllabus of this year. So it will not be in the exam. You won't be examined on the MFCC features. So MFCC features are essentially the energies. So it describes the energy in the corresponding frequencies, and it describes how much. So for example, if you hear these speech samples, these kind of features describe how much your eardrum would be vibrating according to the impacts of this speech feature. So this kind of feature, according to the speech sample. So this kind of feature describes the impacts towards the humans in a way that approximately simulates how humans will hear these features, how humans will hear the sound. So let's take a look at a simplified system. So let's assume that first each word has one and only one sound, X. So this is a simplification that we are going to drop in next system. And the other assumption is that each speech sample, X, contains exactly one word. So I'm going to keep assumption A2 for this system and the next ASR system. So in this simplified system, with these two assumptions in place, then speech recognition can essentially be done by a maximum similarity search. So we collect a large dictionary containing of how every single word in the vocabulary sounds. So when we hear a speech sample, we can just compare that speech sample to every single entry in our dictionary and take the maximally similar item as the recognized word. So this is essentially a maximum similarity search. We have the samples of a word, we query for the samples and find the word that has the maximum similarity with the speech sample. So practically, the assumption one does not really stand, because each word might have different sound, and so different people will speak a word in a different manner, and even the same person will speak a word in different manners. There could be different speeds, and there could be different pitch, and also the amplitude might be different, which means the loudness are different. And also the device that you use to record the speech are different as well. So recording through the speech data sample recorded through one microphone is very likely different from the data sample recorded through the other microphone. So let's use an acoustic model to compute the probability of the sound given the word. We call this conditional probability the acoustic model. So with this assumption, this speech recognition system then becomes a maximum probability search. So we want to find the word in our vocabulary that maximizes the probability of the word given the sound. So this is still different from the acoustic model that we have. the acoustic model computes the probability of sound given word, but we want to compute the probability of word given sound. So luckily we have the Bayes theorem. Bayes theorem flips between the probability of word given sound and the probability of sound given word. So the left-hand side is it's called the posterior probability, the probability of the word given sound. And this equals the prior multiplied by the likelihood divided by the evidence. And the names are sort of arbitrary, but the point of the different color coding is that the prior probability can be computed by a language model, and the likelihood term can be computed by an acoustic model. So with that two items in place, we are able to do the maximum probability search. Because the denominator P of x does not really matter. It is kept constant regardless of what the word W you are looking at. So essentially, this search is turned into a maximum probability search of the P of x given W, which is the result of the acoustic model multiplied by the result of a language model, P of W. In the relaxed assumption, each word has multiple sounds. I want to comment a few sentences about this relaxed assumption. So speech is a communication channel. So in a channel, you transmit some information. But during the process of transmission, the contents might be corrupted by, for example, the noise or the imperfectness of the microphone. And there are also many different ways to speak. For example, sometimes you speak louder, which gives the sound a little bit more loudness and larger amplitude. And sometimes you speak a little bit higher, which gives a pitch that is higher, and the frequencies are higher as well. So there are many factors that make this channel noisy. So by noisy, I mean that each word could correspond to multiple sounds. So the process of generating a sound based on the word goes through a noisy channel. So this process is noisy. And the speech recognition model needs to reverse this noisy channel, and it needs to infer the word based on the noisy sound. So this is why this model is called a noisy channel ASR model. So when talking about noisy channel ASR model, people usually refer to the model that can be computed by the Bayes rule. Actually, this kind of models might appear similar similar to the machine translation models. The machine translation models are also referred to as the noisy channel models, because the process of converting, for example, from English to French or from French to English is also a very noisy process. So each English word, each English sentence could correspond to multiple French sentences and vice versa. So noisy channel models could apply there as well. And since around 15 years ago, these kind of problems are frequently addressed by sequence-to-sequence models. So by sequence-to-sequence, they just mean that the input are a sequence of text and the output are a sequence of text. And this sequence can be more than a sequence of text. It could be a sequence of features, or it could be a sequence of sound. So you can see that the speech recognition models and the machine translation models are very, very similar. They are both sequence-to-sequence models. But because the nature of the data are very different, the systems for speech recognition are designed in some different ways. So since around 3 years ago, these problems are frequently addressed by transformer-based models. And actually, in before 2020, this kind of sequence-to-sequence models are usually based on recurrent neural networks, including the long short-term memory. But now many of these problems are addressed by transformer-based models. So let's elaborate more on the speech. So speech are essentially oscillations. So you can plot the oscillations on the figures. So the x-axis are the time axis, and the y-axis are the locations of the oscillator. So on the plot, you can see that there are a lot of different types of oscillations going on. There is the very high frequency oscillation, and there is also a lower frequency oscillation that gives the oscillation plot this kind of periodicity. So the oscillations at different periods or different frequencies are superpositions towards each other. So which makes this kind of time domain plot very, very noisy and very hard to analyze. So in 2 slides, I'm going to describe some methods to analyze the speech in a clearer manner, which is to analyze in the frequency domain. The one-dimensional speech data are not necessarily the best input for the ASR systems. So sounds are time-variant pressure waves created by vibration. So in the microscopic world, you can say that the air particles hit each other and setting each other's in motion. And in the macroscopic world, we use pressures to describe. So sometimes there are compressions in the air, there are rarefactions in the air. And these types of compressions and rarefactions constitute of these vibrations that you can see from the plot. So 2 of the very obvious features of sound include amplitude and frequency. So amplitude essentially means loudness. If the oscillation has higher amplitude, then that means that this corresponding tone is louder. And if this sound has a higher frequency, then that will appear higher. So here are 2 examples of a lower frequency high amplitude sound versus a higher frequency low amplitude sound. So let me try to play the lower frequency and high amplitude sound. So here, and here is the higher frequency low amplitude sound. So the amplitudes, the difference in the amplitudes are not that significant, but you can hear that these 2 types of sound have different frequencies. So as I have just mentioned, the time domain plot or the oscillation plot you see on the top of this lecture or top of this slide is very noisy. There are a lot of different types of oscillations that are superimposed to each other. So it's very hard to analyze. And what people commonly do to extract some features is to first take a frame and compute the spectrum of the oscillation in this frame. So in the spectrum, there is the x-axis is described in terms of frequency instead of the time. So the spectrum captures the amplitude at different frequency bands. It essentially captures the energy in the oscillation. So if you look at the spectrum plot, you can infer how much energy this oscillation has at some particular frequency. So how to compute the spectrum, or how to go from the time domain to the frequency domain? The standard procedure is Fourier transform. And the Fourier transform is not going to be in the exam. And I'm just going to briefly explain them for informational purpose. So Fourier transform essentially computes computes the spectrum of this signal. And some very nice properties of Fourier transform is that it's invertible. So you can go from the time domain to frequency domain. You can also go back using the inverse Fourier transform. And also it's linear. So when you scale up in time domain, it also scales up in the frequency domain. And it also has the Parseval revelation, which means that the energy in the time domain equals the energy in the frequency domain. So you can study the energies in the frequency domain and use that to represent the energy in the time domain. And this makes it a lot easier to compute the energies in the oscillation. But one problem with Fourier transform is that it requires continuous input. So in the real world, whatever we record from our microphone are discrete input. So although we have as many as 16,000 numbers per second, it is still continuous. So what people actually use is discrete Fourier transform. And DFT is very similar to FT, except that we do not use integration, we use summation. And the terms are a little bit different as well. So the discrete Fourier transforms are usually implemented in popular packages. So you don't really need to memorize the equations for the Fourier transform or discrete Fourier transforms. And to implement the probability of sound given word, we can use a lot of different types of models that model the distributions. So it can be some non-parametric models, it could be some Gaussian models, it could be a neural network that predicts the probability of sound given word. So whatever model that you use to approximate the distribution depends on how you understand the training data. So the training data usually includes a lot of different people speaking different words. So for each word, there can be multiple corresponding X, and there could be only a few X that correspond to that W. So the distribution is high dimensional, and the distribution is usually hard to approximate. So the acoustic model is not very easy to implement. And which model that you choose to implement actually reflects how you think about the data and the nature of the data, actually. Question?
Yeah, so, sorry, so with Fourier transform, we're transforming like a 1D array into like a 2D one. So by like we're measuring the like voice data with like the amplitude at different frequencies. That's how it's done.
So Fourier transform.
Yeah, so like with Fourier transform, what we actually transform the 1D array into, like.
So essentially, it also transfers into one-dimensional, but the dimensional is different. So in time domain, the one-dimensional is time, but in Fourier transform, after you do the Fourier transform, the one-dimensional is frequency.
Oh, so we're just transforming
time into frequency.
Okay.
Yes, yes. And also because the time aspect is removed, people usually look at the frames. So we only do the Fourier transform within this frame instead of the whole speech sample. So actually, in extracting the features, the features actually describe the oscillation energy at different corresponding the frequencies. So it approximates how much your eardrum will oscillate at different frequencies of this sound speech sample. So actually the details are in the MFCC features, and if you're interested, you can check out the MFCC features, and they are doing that in a very clever way. But the MFCC feature is not in the syllabus of CAC 401.
Yeah, but if we transform from the time domain to the frequency domain, it's no longer a sequential data, right? Then why are we still using transformers to do this?
It is still a sequential data. So actually, because you are segmenting them into frames, each frame is represented by one vector.
Oh, okay.
So you still have sort of this kind of sequential structure, but the sequence length is much shorter, and each sequence is represented by multiple features.
So how is the frame separated?
It's usually just 50 milliseconds.
Oh, okay.
50 milliseconds, and at the end of the frame, there are some special methods to take care of the separation, so that you don't have the sudden jump across the frames. Yeah, so by the end of this lecture, you should be able to answer what is speech recognition. So automatic speech recognition is a crucial component in the modern smart assistant, and it essentially translates speech into text. And speech are essentially some oscillations, and this kind of oscillations can be recorded in one-dimensional numbers and one-dimensional arrays. And this kind of one-dimensional arrays are usually extremely long. So there are some features in the speech, for example, amplitude, how large or how loud this sounds, and frequency, so how high is the pitch, and also spectrum. The spectrum of the speech features sort of describes the how much energy is present in the corresponding frequency. And we also describe some noisy channel models for speech recognition. So there are two assumptions. A1 is that for each word, there could be multiple sounds. And the assumption 2 is that each speech sample only contains one word. So the input is the speech sample of one word, or the extracted features thereof, and the output are the corresponding words. So the noisy channel ASR model is one of the simplifications of the models. And in order to look at a non-simplified version, let's take a look at the so-called LAS model, which I'll describe on Wednesday. So that concludes today's lecture. See you on Wednesday.